The reason we're here today is Professor Andrew Blakers from the Australian National University. He's the man with the waves behind him. Professor Blakers is with the university's Research School of Electrical Engineering and Materials Engineering, Electrical Energy and Materials Engineering in the College of Engineering and Computer Science. Professor Blakers is the director of a university centre for sustainable energy systems and employs some 60 staff. He's responsible for several innovations in solar energy photovoltaic technology, including sliver cells. I'm not sure what they are. Someone who is going to be at today's meeting is not here, unfortunately. I don't know where he's got to. Asked Andrew a while ago about green hydrogen, and Andrew said that was a job for the 2030s. He said, what's more important is in the meantime, we can get on with eliminating coal from electricity production, oil from land transport, and gas from heating, which yields emission reductions of 80%. That's after getting rid of fugitive methane emissions from coal, gas, and mining. Anyway, we can't actually applaud Andrew as such, but let's give him a round of applause and welcome him. Over to you, Andrew.
Okay, so I'll share my screen. And you'll have to just let me know if it's successful.
That should be right.
So is it shared?
Yep. You've got your previous little slides in. That's better.
All right. Okay, so I'm going to talk about renewables and storage for about 20 or 25 minutes, and then we can have a discussion if that sounds right. Yep. Feel free to interrupt if you need to, and let me know if I suddenly go offline for some reason.
Sure.
So the first point to make is that solar PV, solar photovoltaics and wind have won the energy race. So this is a graph of the global annual net new generation capacity over the year 2015, 16, 17, 18 and 19. So as you can see, PV and wind are very far ahead of anything else. Hydro is declining because we're running out of rivers. Nuclear is going nowhere. Bio is going nowhere. Solar thermal, geothermal, tidal, wave, all the rest are just lost in the noise. Gas is hanging in there because of its ability to peak. Coal is on the way out. In fact, if you took out China, coal has gone negative. In other words, coal plants are closing faster than they're opening. It's only China that is keeping coal above water. So PV and wind won the energy race because they're the cheapest. So wind, there is plenty of wind around the place. Wind turbines just keep getting cheaper and they keep getting bigger. And there are more and more going offshore where there is unlimited space and you avoid the clash with land values. So there's one very large wind farm proposed for Bass Strait, Star of the South. But you know, the really big places for wind farms are going to be the North Sea and the Sea of Japan. So this is a map of wind power potential. The redder, the better. So Australia is not bad for wind power. It's got a lot of land, a lot of pretty good areas. But basically, the further north and south you go in general, the better the wind, but also the fewer the people. So wind is just pretty good for the Northern Hemisphere where the sun is pretty bad. So solar photovoltaics won the solar race, hands down, over solar thermal. And the interesting thing is that exactly the same device, which is the silicon solar cell, is used for a micro system in, say, Cootagita National Park or on top of a mountain or at a remote lighthouse or the tourist resort or at the Royalla solar farm, 20 megawatts, or 100 megawatt solar farm or 1,000 megawatt solar farm. So it's basically the same device. And this gives enormous ability for the PV industry to scale up because it's just the question of what you do with the solar cell is simply a matter of packaging. Do you want a big set of modules or do you want a little set of modules? Unlike a nuclear power station where you can't package up a 1 kilowatt or a 1 megawatt or a 1 gigawatt, it's all got to be at the gigawatt scale. And similarly for gas and coal and hydro. Australia is the global renewable energy pathfinder. We're installing renewables much faster than anybody else. And so the red bar is the watts per person per year of new renewables. It's all PV and wind installed in 2018. The green bar is in 2019. And as you can see, Australia is installing wind and solar PV about 4 to 5 times faster than Europe or Japan or China or the USA, and about 10 times faster than the global average. So through an accident of history and completely contrary to government preferences and policy, the compelling economics of wind and solar in Australia is running right over the top of policy and is causing Australia to be the global pathfinder. So plenty of people live in the Sunshine Belt. That's plus or minus 35 degrees of latitude. That's all of Africa, almost all the population of Australia and South America and Central America and India, a large part of the population of China, Middle East, Southeast Asia. So about 3/4 of all people live in the Sunshine Belt, where there are no cold winters, and the winter sunshine is not very much different from the summer sunshine, and so you don't need seasonal storage, which is quite an important point. For those people who are almost all in the Northern Hemisphere who live outside the Sunshine Belt, that's about 1 billion people in Europe and Northeast Asia and Northeast United States, Canada. For those people, they've got wind. So everyone's got PV or wind or both. Australia's got both, and many other countries also have both. So solar PV and wind constitute about 2/3 of net new global generation capacity. That's because they're cheap and they're getting cheaper. They provide stable and reliable power when you spread them out over a whole landscape, so that a local cloud doesn't matter very much. Nearly everyone's got good access. Importantly, we'll never go to war over solar and wind energy because everyone's got it, unlike oil. There's vast resource availability until the sun becomes a red giant. We can eliminate most greenhouse gas emissions by getting rid of oil, gas and coal. By most in Australia, I mean 85%. Around the world, it's a typical average of 75%. There's an infinite supply of raw materials. A solar panel is made of silicon, plastic and glass, an aluminium frame. We can't possibly run out of those raw materials. And one of the wonderful thing about solar is that there's no radiation leaks, no oil spills, no fracking, no strip mining, no coal mine fires, no smokestacks, no car exhaust, no smog, and it's useless for warfare, terrorists or criminals. We solve an awful lot of problems when we go to wind PV energy supply. So how do you stabilise a 100% renewable electricity or energy system? Well, the first thing is PV and wind go well together. The wind often blows at night. The sun never shines at night, so that's pretty good. If you spread them out over a large area, like 1 million square kilometres, such as the East Coast National Electricity Market, then you hugely reduce the amount of storage you need by smoothing out local weather. So local wind lulls or local cloud doesn't matter very much. You can just import wind or solar electricity from somewhere else, and when the sun comes out and the wind starts blowing again in your area, you return the favour. Demand management is energy 101. You just stop shifting loads from day to night, as we do with off-peak water heating, and shift them from night to day. And you can have interruptible loads, such as an aluminium smelter, so that if you're short of energy, you can just turn off the smelter for a few hours or a day, and use that energy, divert that energy to a more pressing need. So this is just very straightforward application of power electronics. And finally, you do need mass storage, and there's only 2 shows in town. That's pumped hydro, which is 97% of all storage, and advanced batteries. So let's talk about wide area transmission, and it can be AC or DC. DC stands for direct current. So long distance greater than about 800 kilometres, you're better off with high voltage DC running at hundreds of thousands of volts, or for shorter, you probably go for high voltage AC. So Adelaide to Wagga is right on the cusp of whether it's DC or AC, but they've chosen AC. If you go underwater, such as a Marinus link to Tasmania, you choose DC. State of the art is running at 1.1 megavolts over 3,000 kilometres, which is Adelaide to Perth and more, at a power of 12 gigawatts, which is half Australia's average power output, with a 10% loss, in a cable that's about 15 centimetres in diameter, plus cladding. So this is, you can really do transcontinental interconnection with very low loss at very high power levels. So as I mentioned, storage is almost all pumped hydro with a little bit of battery on top. Batteries are growing, but they've got a long way to go to catch pumped hydro. I'll talk a bit about pumped hydro. So this is conventional pumped hydro, where you've got an upper reservoir. This is Tumut 3 power station, and a lower reservoir, and the water can be pumped from the lower to the upper, and when there's excess PV and wind, and in the middle of the night you can let the water come back down through the turbines. So the same turbine acts as a pump if you put electricity into it, or a turbine if you take electricity out of it. So the upper reservoir you see there is actually the lower reservoir of famous Snowy 2.0, and the upper reservoir of Snowy 2.0 at Tantangara Dam is about 20 kilometres off to the left. So this is existing system is a 1.5 gigawatt power rating. Snowy 2.0 will be 2 gigawatts. But there's vastly more opportunity away from rivers, and this is a good example of an off-river pumped hydro system in Presenzano, Italy, where you have two artificial reservoirs, the upper and the lower, separated by 500 meters in altitude and connected by a tunnel which contains a pump turbine. And the water just goes backwards and forwards between these two reservoirs. It's got a storage time of about 6 hours, running at its rated power of 1 gigawatt. And we've done a global atlas of all pumped hydro opportunities around the world. We've found more than 600,000 of them, with 23 million gigawatt hours of storage potential, which is about 100 times more than you would need to provide a 100% global electricity system when everyone uses the same amount of electricity per person as Australia. So there is unlimited off-river pumped hydro opportunities around the world. We can't possibly run out of them. And all of these sites are outside national parks and urban areas, and none of them are on rivers. So in Australia, we found 3,000 good sites, 163 terawatt hours of storage, which is about 300 times more than we need to support 100% renewables in Australia. Let's zoom in a little bit more to the southeast part of Australia. The top left, we can see Shepparton in the mid top left. Let's zoom in a bit more. Shepparton is now the top left. And as you zoom in on your atlas, you can go and explore this atlas afterwards. You can see the individual reservoirs resolve. The dots are on the tunnel route, and they refer to how good the reservoir is from a cost point of view. So the redder the better. And the red arrow at the bottom left just points to one example, which I'll zoom in on now, at Yark. So you keep zooming and you end up with this detail. You can see the upper reservoir, the lower reservoir with 30-metre resolution laterally and 1-metre resolution vertically. You can see the dam walls at the lower end of each reservoir. You can see the tunnel route, and if you press on the red dot, which says this is then you get a pop-up which says this is an A-class reservoir pair. In other words, it's a pretty good one. Head, that's a height difference of 350 metres, separation of 3 kilometres, an average slope of 12%, which is good, which means the tunnel is shorter and steeper. It's 15 gigawatt hours of energy storage, which is quite a lot. If you had 30 of these in the whole of Australia, then you'd have enough storage to support 100% renewables in Australia. And it's got a water to rock ratio of 9, which means that for every gigalitre of rock that you move to make the dam wall, you'll store 9 gigalitres of water. So overall, when you do the sums, that is a pretty good site. And there's hundreds of these sites around Australia. So as I mentioned, all the pumped hydro sites we found in our outlets are outside national parks and urban areas. The combined reservoir area required is about 6 hectares per gigawatt hour. That's about 2 square meters per person to support 100% renewables. In other words, the area of lake for the pumped hydro required to support 100% renewables is about the same as a slightly large bathtub. So we are not going to be short of land, short of opportunities to find lots and lots and lots of pumped hydro opportunities anywhere in the world. And the area of land required for the reservoirs is 10 to 15 times smaller than the corresponding area of wind and solar farms that it actually supports. And it's also vastly smaller than river-based hydro.
Ask a question. Is the 2 square meter per person, is that are there existing, well, there are existing reservoirs?
Almost no existing reservoirs are interesting because they tend to be in national parks if they're steep country, and if they're not in national parks, the country is not steep, which means that the upper reservoir has to be a long way away, which means the tunnel has to be long, which makes it expensive. So most of the interesting reservoirs are in steep, hilly agricultural land, away from rivers, away from existing reservoirs.
No, but you talked about the 2 square meter per person, but the example you showed already had the reservoirs there. So is that included in 2 square meter?
There's a what, sorry?
This example is already there, is it?
No, this is an image superimposed on the landscape. This doesn't exist.
Oh, there is no reservoir, okay.
No, this is, when you go to our website, you can explore as you wish over anywhere in the world.
Yeah.
And just focus down on anywhere that's interesting. And you'll, as you keep zooming in, you'll see the screen, and eventually each of these dots resolves into a synthetic image of an upper and lower reservoir and tunnel and dam and pop-up.
Okay, yeah.
So the water requirements for pumped hydro are really small. They're about 10 litres per person per day, which is equivalent to 1 minute of an average person's shower. And that includes for the initial fill and evaporation. And it's much smaller than the amount of water that goes up the cooling tower of an equivalent coal-fired power station. So all around the world, there's large multiples of available off-river pumped hydro compared with actually what's required. So the little table there shows that for various places, the available storage in gigawatt hours compared with the required storage to support 100% renewables in each of those jurisdictions. So you can see it's a very large ratio. So what other options are there? Well, there's batteries. The Hornsdale big battery is 0.1 gigawatts, 0.13 gigawatt hours. So that's actually just been uprated to 0.15 gigawatts and about 0.2 gigawatt hours. Compare that with Snowy 2.0, which is about 15 times bigger in power and 1,000 times bigger in energy. So batteries are interesting for low power, high power, short duration storage, very rapid response ranging from sub-seconds up to about an hour. And pumped hydro complements batteries for hour to days of storage. Home batteries are very small. They're only about 10 or 15 kilowatt hours each. And even if everybody in Australia has one in their home, it'll be peanuts in the overall scheme of things. Much more interesting are car batteries. Instead of 10 or 15 kilowatt hours, an electric car battery is 50, 60, 70 kilowatt hours. So it's 4 or 5 times bigger. And it's paid for anyway because you bought the car for transport. And so the extra storage capacity essentially comes along for free. So this is a seriously interesting complement to pumped hydro. So I mentioned before that strongly interconnecting states with high voltage DC and AC is a very good idea because you reduce the amount of storage. Well, we looked at the amount of storage you need to support 100% renewables if each Australian state went it alone with no interchange of energy across borders. And so you need about 2,000 gigawatt hours with a power of more than 60 gigawatts. as soon as you put in some strong interconnection between each state, you get a huge reduction in both the storage energy, that's the size of the reservoirs, and the storage power, which is the size of the pump turbine and tunnels. And if you include electric vehicle car batteries, which effectively have 24-hour storage, because you don't need to charge every day usually, then you halve it again. And you can get down to really modest amounts of overall storage required to support 100% renewables at low cost. And so this little graph in US dollars shows the balancing costs for various fractions of renewable energy, where most of it is wind and PV. So the balancing cost comprises the storage, the extra high voltage interstate transmission, and occasional spillage of wind and solar when you are running at, when you've got windy, sunny weather and the reservoirs are all full. So obviously at no renewable energy, you'd need no balancing cost. You can see that most of the costs come between 80 and 100% renewable energy fraction. And right up to 70%, it's only costing you about $5 a megawatt hour, which is about 10% of the current wholesale cost of electricity. So people who spout on about the high cost of balancing renewables don't know what they're talking about. A lot of nonsense is talked about the alleged difficulty of getting to high levels of renewables, and most of it is written by people who live in the north of the planet. So people in Europe, Northeast Asia, and Northern America, where there are cold, bitterly cold winters with almost no sunshine, and they just throw up their arms and say, this is all really hard. Well, most of the world's population doesn't live in that sort of place. It lives in the Sun Belt, and Australia is a Sun Belt country, and we're much more like the Sun Belt than the North, and our view of things is much different, and it's obvious from what's happening in Australia that it's actually not very hard at all to get to high levels of renewables, and we're demonstrating it right now. Excuse me a moment. So we have low latitude, and the solar resource is excellent, and the seasonality of solar is low. There's almost no variation from summer to winter. We've got good wind. The Sun Belt has good in parts. We've got a low heating load and no need for seasonal storage. And we have large numbers of pumped hydro sites. We're a high wealth country, which makes it easy in one respect. But on the other hand, we have a large amount of current fossil fuel capacity, and that makes it difficult because we have a very powerful vested interest, a fossil fuel mafia, which dominates the right wing of the Liberal Party and is strongly supported by the Murdoch press, who then spout lots of nonsense about how tough it is to do anything with renewables and how we're much better off with new coal power stations. But the fact is that despite, not because of, our current federal government, we are renewables pathfinder. So we have the highest amount of solar PV deployed anywhere that compared with anywhere in the world on a per capita basis. We're putting it in faster than anybody else in the world on a per capita basis. We're putting in solar and wind combined faster than anyone else on a per capita basis. And we're doing this because we're a high income industrialized country where the compelling economics of PV and wind are winning out over coal and gas, despite the fact that we're not electrically connected to any other country, because we are a Sunbelt country, which is the same as where 75% of the global population lives, and despite the fact that we're #1 for coal exports globally, #2 globally for liquefied natural gas exports, and #4 globally for uranium exports. So we're doing it despite the vested interests that are bitterly opposed to renewables.
Isn't there a few other reasons, like our electricity costs are one of the highest in the world from the traditional suppliers?
Well, I'm not sure where they get that number from, because it's complete nonsense. It's completely wrong.
That's wrong, okay.
I mean, it's just complete nonsense. The average wholesale electricity price in Australia so far in 2020 is in the national electricity market, which is 80% of all Australians down the East Coast, is $40 per megawatt hour, and that's among the lowest in the world.
Okay.
It's complete and utter moonshine. I don't know what they've been drinking.
Okay.
So it's people who know, quote unquote, that renewables are expensive and don't bother to go and look. You know, they have factoids from 10 years ago and assume that what happened 10 years ago is still valid today. So electricity is straightforward. We can get deep emission reductions through getting rid of coal generation from electricity. Electricity is 36% of emissions at the moment, greenhouse emissions. The next step is to push oil out of land transport and get rid of oil imports. And that allows us to eliminate another 13% of emissions with nothing to invent. It's simply just ever improving technology of electric vehicles as we scale up into the many multi-millions and then tens of millions of EVs. The next thing is also completely off the shelf. That's using heat pumps to get rid of low temperature gas heating for air and water. That's another 7% of emissions. And we're very close to break even now in pushing gas out of high temperature industrial heating beyond the range of heat pumps, which is another 11%. Getting rid of fugitive emissions at 10% means that we can make a 75% cut in emissions without inventing anything new. We just need to go out and do it. And then that leaves for the 2030s and 40s, the remaining sectors, which is industrial processes. That's basically ammonia synthesis, cement, plastic synthesis, maybe synthetic jet fuel for aviation, and ammonia for burning in ships, and agriculture, which everyone knows is difficult. But we have this low-hanging fruit of 75% of emissions, which we can just go out and do in the next 10 years.
Andrew, could you just unpack fugitive emissions a little bit, please?
Yeah, that's methane emissions from coal and gas mining. So if we stop mining it, then the fugitive emissions go to zero straight away.
Great, thanks.
So it's all easy, 3/4 of emissions. And PV and wind are the only credible way to eliminate fossil fuels, which are responsible for 80% of Australia's greenhouse gas emissions. It's not very hard. It really isn't. And we're well on our way to do it. So this is a pathway to 100% renewable energy, not electricity. Roughly speaking, we need to treble electricity production in order to push fossil fuels out of everything, transport, heating, and industry. And we need to make sure it all is coming from wind and PV. So what you see there is the gigawatts of new capacity per year installed for wind and solar in Australia by year, 2015 through 2019 in the green bars. 2020 and 21 are my estimates of what will happen in the next 2 years. And the red bar is where we need to be from, say, 2023 in order to get to zero emissions in 2050. In other words, eliminate all oil, gas, and coal from the economy by 2050. And we multiplied by 6 our installation rate between 2015 and 19. We merely need to double it over the next 3 or 4 years. And then that places us on track to have a zero emission society in 2050. It's not very hard. So in conclusion, PV and wind are 2/3 of global net new generation capacity. They won the race. Coal and gas can't compete on price, and it's only a matter of a few years before PV and wind compete not only with new build coal, but undercut the operational cost of existing coal. That's the fuel and maintenance. And you're going to see a wave of premature coal power station retirements in Australia over the next decade, despite the best efforts of government. Deep renewable electrification can eliminate 3/4 of greenhouse gas emissions at about zero net cost over the next 20 or 30 years, fast enough to stay at 1.5 degree warming. Transmission and storage are really critical in order to smooth out local weather and to provide storage opportunities. We need no heroic assumptions about future technology developments. We just focus on PV, wind, high voltage DC, AC, pumped hydro and batteries, all of which is in 100 gigawatt and above deployment already. And the Sunbelt countries can simply skip fossil fuels and go directly to PV and wind, where 3/4 of the world's population lives. And that's it. Thanks.
Well, thank you, Andrew. Andrew, is there anything an individual can do, or do we have to depend on the government to change things?
Oh no, be subversive.
Be subversive.
Yeah, go and put more PV on your roof.
Yeah.
Put more insulation in. I mean, it's extremely effective. Australia's now got 12 gigawatts of rooftop PV. That's more than any other country, not accounting for population. We are #1 in the world for rooftop PV. And this is hugely destabilizing coal power stations. It's just wonderful. So the more PV goes on your roof, stuff as much as you can on the roof as you can. Firstly, you save money. And secondly, it's a direct strike against the anti-renewables policy of the federal government.